Airport runway lighting. In this presentation, we're going to be looking at an introduction to the system, types of runway lights, system components, system operation, system design, safely maintaining these things, and finally some information at the end regarding training and certification for airfield lighting. Airfield runway lighting systems are highly regulated specialty applications. The standards for the equipment installation are very high. All equipment is specifically designed for airfield applications. The circuit design and power supply is different when compared to any other sector of the electrical industry, and overcurrent protection is not part of any airfield lighting system. In 2014, the Calgary International Airport completed construction of a second main runway. The lights outline the runway, and that circuit for the lights is approximately 14,000 feet in length. There are 180 runway lights in this circuit. So the question comes up, is the circuit designed as series or parallel? Now, for reasons that we're going to go into, they're actually designed as a series circuit. And if we take some of these basic values for a standard runway light, approximately 6.6 amps, 13.2 volts each, they appear to operate on a fairly low voltage. Now, if connected in series, each light will receive an identical voltage due to the equal sharing of potential on identical loads in series. This means each light will receive exactly the same current, 6.6 amps. Now, of course, for each of them to get 13.2 volts, you're going to need a source of 2376 volts. Now, equal levels of current mean equal brightness at each light. And this means that for the pilot that's landing the aircraft, there will be a consistent visual, and it will reduce any form of confusion with lights being brighter in different areas or not. Airfield runway lighting systems are designed as a high voltage series circuit. The system is extremely unique as the high voltage source automatically maintains a constant current through the system. The lights are connected to the series circuit through individual isolation transformers. And the primary purpose of airfield lighting systems is to aid in the landing of aircraft. Larger airports require more extensive and complex airfield lighting systems. The ability of an airfield to land aircraft in adverse weather conditions is known as its CAT, or category rating. We can see in the below illustration a very simple approach and runway lighting system. As the CAT rating gets higher, we'll start to notice that there are more requirements with more lights and more approach lights even before the runway starts. All of these are to ensure that aircraft are able to land when the weather conditions are poor and if their instruments on board were to fail. Here's a better illustration to show some of the different lights. Each one is specifically designed and angled at a specific level in order to target approaching aircraft. Even taxiways, where the aircraft is coming on and off of the runway, have specific colors and locations that are required. Each light on a runway is designed for a specific purpose. Their position, color, brightness, and coverage all have significance when viewed by the pilot of an aircraft. The requirements of airfield lighting is found in Transport Canada, FAA, and military specifications. Runway lights are probably the most common form of light on an airfield runway. Airfield runway lights are designed to show the outline and sometimes the center of a runway. Runways are used exclusively for airplane takeoff and landings. Here's another one with a fluorescent pole beside it to make it obvious for snow clearing and groundskeeping equipment. And then we have some lights at the end of the runway here. One of them is going to be green, the other's red, and that's to show the start and the end of a runway, depending if an aircraft was landing or if it was taking off. There's also recessed runway surface lights. These are recessed or inset into the center line of a runway. They require cleaning over time as aircraft tire impact can leave rubber streaks obscuring the lens. When working with any airfield equipment, extreme attention to detail is important. A missing or lost bolt could result in damage to an aircraft on takeoff or landing. Taxiway lights are the second most common. Airfield taxiway lights are designed to show the outline of sometimes the center of a taxiway. And taxiways are areas where aircraft use to travel from the airport terminal to the runway. There are going to be all sorts of different colors and different indications. Elevated runway guard lights, these are at the entrance to a runway. These are meant to provide obvious indication for a pilot that they need to stop there before they proceed onto the runway from a taxiway. Usually, they're given the permission from the air traffic controller. These lights are a little different than some of the others that we've looked at. These oscillate or wigwag from left to right. Approach lights are on the landing approach prior to the start of the runway. The height and angle is different for each set of approach lights as per airfield regulations. There are typically multiple rows of approach lights to direct our aircraft to the airstrip. So here's an example of some approach lights, and depending on the category rating, we can have more or less. Depending on the system, a series of strobes on the approach light bars will flash in sequence to guide the aircraft in to land on the airfield. Historically, most runway lighting systems have been halogen or incandescent. These bulbs are specialty application and cannot be typically purchased at the local wholesaler. As technology has advanced, LED has started to infiltrate the airport sector. Unfortunately, LED is not always the best choice. And specifically for Canada and Northern Canada, we can see that there is the addition of a requirement to provide a little bit of heating. So if you look at the top of that board, there's some blue resistors, and those are being used as heaters. This particular system requires an Arctic heater board. This ensures that the snow melts from the fixtures during a snowstorm. Keep in mind, any efficiency gains are now lost due to the need for an auxiliary heater. PAPI are another type of lighting system that we see at airports. This is a precision approach path indicator. This is used to assist pilots in determining their approach altitude while landing. They include high output bulbs and a lens, sometimes that's polarized. Notice that each bulb in this setup is individually connected by its own isolation transformer. They are not connected in parallel, which is what you might expect if you came to this from a different sector of the electrical industry. So these are high intensity lights which are directed through polarized lenses. If working close in proximity to these at ground level, the light is strong enough to burn clothing and damage eyes. The position of the PAPI is precisely determined by a surveyor when the airport is first built. Replacement of the unit due to damage or readjustment or adjustment of all supporting legs may require a resurvey. And so that means that you don't adjust all three legs because over time, vibration and things, these will need to be adjusted. Now, what we can see on the right-hand side here is what the pilot would see. There are many different types of approach lighting systems, but this particular one we can see with 4 lights that's shown will be indicating different colors of lights to the pilot, depending if they are low, perfect in altitude, or too high. And here's the leg height adjustment, ensuring that we only adjust 2 of the legs if there are 3 present. Never adjust all 3. Here's a 4-light PAPI indicator with a plane that's approaching at its proper altitude. And what you'll notice is that there's 2 reds and 2 whites. If that object is off position and has not been leveled off correctly, then the indicators for the approach altitude will show maybe 1 red and 3 white, or 3 red and 1 white. That will throw the pilot off because they'll be trying to confirm this with the instruments they have on board. Omnidirectional lights are high-power strobes. They're very large and strategically located as per airport regulations. These use specialty high-intensity flash bulbs. They're usually over 1.5 foot in actual height. Now, lights, location signs, and light towers can all be damaged from aircraft, snow removal equipment, and grounds equipment, such as mowers. All equipment on the airfield is designed to readily break away from their supports if damaged. This is to ensure minimal damage occurs if impacted by an aircraft. Aircraft are fragile and potentially full of jet fuel, and let's not forget people. Due to this, most of the equipment is going to be built with a frangible fault line where it's engineered to break away at a predetermined amount of force. Location signs. This is an example of an LED flat panel location sign. There are many different types out there depending on the era of airfield that you happen to be working at. Here's another location sign where it's a beginning into the technology of optical fiber, but really basic optical fiber, where there's a light bulb which is directed or focused through a lens onto a, well, fiber line or fiber optic. And we can see inside here that we actually have the light bulb on the left, and then it's shining in to all of these individual strands, which are on the other side of this unit here. And you can see all the black strands. They're just, well, fiber optics, and then they've been poked through to the front face of the sign. So depending on what era of airfield we work at, there's a whole range of different legacy and new equipment. A basic runway lighting system consists of a constant current regulator, which is the source, isolation transformers, which are in end pulpits, lights, and single high voltage conductors, as well as sometimes a counterpoise ground conductor. The pulpits are a plastic or metal housing below ground used to contain the series isolation transformer and facilitate connections to high voltage series circuit conductors. They can look like this, plastic with an open bottom, or they can be metal with an entirely closed bottom. On the left is an existing pulpit with isolation transformers and connections. On the right is one that's just above grade while it's being used for demonstration purposes, but you get an idea as to the size of the unit. The high voltage cables are running conduit typically, but the cables are rated for direct burial, usually in a bed of sand, and the cable is then run between pulpits. The high voltage cable is specific for a system that operates at about 5 kV. It is called ASLC, and that's Airfield Series Lighting Circuit Single Copper Conductor Cable. It can be found in the CEC. Sizes range from number 10 to number 2 AUG based on the circuit length. All connections are weatherproof, direct burial rated, single pin and sleeve design. And so that means we're not doing any permanent sort of splices. Everything has a connector on the end where it then slots or mates into its comparable mate, as in male into female connector. We can see down here a male connector, and this is the female connector. That plastic part would come out after the connector had been fixed to the cable. The series isolation transformer connects to the light with a two-prong connector. It then connects to the high voltage series circuit through two separate male and female connectors. And so we can see here on the diagram on the right an in and an out, and then the two-wire cable with the larger sort of knob at the end here, that's going up to the light itself. Each runway light is supplying power or supplied power by its own one-to-one isolation transformer. The transformers are submersible rated with no serviceable parts. And if we take a look at the nameplate, they're kind of interesting in that they show both the primary and the secondary of equal amperage, and that's because in airfield lighting, the airfield lighting circuit has a maximum illumination at 6.6 amps, and that's an international standard. So this is a one-to-one, as in the voltage that comes in on the primary would be exactly the same voltage that's then generated on the secondary. You'll also notice that the transformer is rated in watts, and that is to reflect the size of light that this transformer can power. So a 200-watt transformer would be able to power a 200-watt runway light. Now, series transformers come in many different physical forms and, of course, as we said before, size to the lighting load they supply. And you can see a number of different wattage ratings shown here. Now, the series isolation transformer is installed in the pole pit. It has two high voltage connections and one secondary dual pin connection which goes to the lamp. There's our high voltage connectors that will then power the primary of this transformer. The runway light is a 2-wire with no bond cable with a 2-prong plug, which connects to the isolation transformer secondary. Lights can be mounted on pulpit lids designed for the purpose, in which case the light pulls threads into the pulpit lid, or, more commonly in Canada, it is mounted on a galvanized stake, and then a PVC conduit takes that 2-wire cable down to the isolation transformer. This can make it a little bit easier to adjust the height if we need the light to be higher off the ground, and to replace the lights without damage to the pulpit if they get hit by a snowplow. Here's a close-up of the angle iron stake or galvanized stake that is driven into the ground, and then the airfield light threaded into the top. You'll notice again that frangible line which is on the connector that threads the light into the housing or the receiver for that galvanized stake. The ground counterpoise is a copper conductor, typically number 8 or number 6 aught. It's uninsulated and buried above the series high voltage conductor in a zigzag pattern when the cables are directly buried in the earth. If, instead, it's pulled into conduit, which would be the preferred method, it's insulated and pulled in the raceways with the high voltage cable. Now, the purpose of this is for lightning protection, so that we don't fry everything in the system when lightning strikes the ground, but it's also used as the bond for the PVC pipe that the high voltage is drawn within, and it connects to every one of the metal mounting stakes, the pulpit, and also the transformer on a split bolt that you can see here that is mounted in the end. So here we have the full connection with the counterpoise that is drawn in through the PVC conduit. It then connects to the isolation transformer and also goes out and hits the galvanized stake, which the airfield light is mounted to. The constant current regulator is the source for this system. It is a single-phase, self-adjusting, high-voltage supply. AC voltage is stepped up to high voltage through a transformer, then precisely adjusted. Now let's break this down a little bit. Constant voltage source would be what we're used to in the electrical industry. A good example is a battery. 99% of electrical sources in industry are constant voltage. That means the source voltage remains constant, and the current increases or decreases with the connected resistance or load. A constant current source, which is runway lighting, is about 1% of the electrical sources in industry. The source voltage automatically adjusts to ensure that current remains constant, regardless of the resistance connected. Now, there are two different types of airfield lighting constant current regulators, abbreviated as CCRs. The first type is an SCR dual or quad controller. These are typically a little bit older and not able to supply LED lighting conversion very easily. They also have high harmonics that are generated. The second type, more modern, is a ferroresonance transformer controller. These are far newer, and they're able to supply LED lighting conversion more easily with lower harmonics. So let's take a look at the first one, the SCR controller. An SCR constant current controller is actually doing exactly what you think it is. It is a controlled AC output, single phase, and it's using two SCRs. They're connected inverse parallel, and that means that it can control the rising positive alternation and the dropping negative alternation of a single phase AC sine wave. We can see here that it can control the voltage going out from here, full brightness, where there's almost no adjustment done to the sine wave, but by shaving off some of the sine wave, we then have less voltage going out, but it's still sort of a sine wave, isn't it? It's still sort of AC. So that's about half brightness, and then you could go all the way down to almost nothing. Now, on paper, it kind of looks rather perfect and elegant. In reality, if we take a look at the Honeywell manufacturer-provided troubleshooting guide, the SCR wave shaping makes for a choppy waveform and significant harmonic interference, which then led to interference with different types of controls, computers, and overheating of conductors, depending on what else was on the system. Here's an example of an older constant current runway lighting regulator bank. And we can see here each one of those bays has a controller in there which has SCRs which will regulate the single phase output. Let's take a look at one. So inside the door, there's going to be either 2 or 4 SCRs. Now those are the monstrous things located on the left-hand side. Now SCRs are thyristors. Down at the bottom is actually the early 80s to early 90s control circuit boards, and each one of the boards will be able to be slid out and replaced or troubleshot. Now some airfields still have these systems, and so it's important to know what you're looking at when you open a cabinet. At the top is a CT, and this is how the system gauges how much current is actually flowing in the airfield lighting circuit. In behind, we have a transformer, and on the very front, we have something called an isolator handle, which we'll talk about in a few moments. Now, why are the thyristors so large? Well, the thyristors are really just mounted on monster heat sinks because they, well, consume a lot of energy. Well, I shouldn't say that. They consume a little bit of energy and they need to get rid of that heat energy without destroying any equipment nearby. And so those heat sinks are there to reduce the heat. Now, the more modern system is a ferroresonant constant current regulator. They use the properties of inductance and capacitance to find a unity power factor at different times to try to adjust or restrict artificially the current flowing through a transformer. It is way too involved for us to go into, and really, it's just going to be a black magic box. That's as far as we're going to take it. You believe me that it works, and we'll all be happy. Now, if we were to take a look at a real one at an airport, it would look something like this. So same idea where it's got a cabinet that opens up, and when we open it, there's a number of different items inside. So we can see here the controls that actually adjust how much of the system is restricting current. A solid state relay is extremely fast switching speed. A transformer is mounted behind the system. A isolation handle, which is something that we're going to again chat about a little bit later, and the capacitors, because this is ferroresonance, they have capacitors and they're trying to adjust artificially the power factor, which will then restrict current flowing through the transformer. Now, constant current regulators, or CCRs, are designed to ensure aircraft land safely in suboptimal environmental conditions by always providing operational runway lights. The system is not designed with the same overcurrent protections inherent to all other systems in the electrical industry. And so the supply, where we power up the constant current regulator, that's obviously a typical feeder circuit, like up here. That's simply supplying power to the CCR. But the output side of the CCR is a different story. There is no overcurrent protection on these wires. Now, work on the series circuit can be done safely if fully de-energized. All CCR systems have an isolation handle designed into the equipment. The device can be removed after the system is de-energized by the main overcurrent device. Remember, that supplies the CCR. This offers a visual confirmation that a system is safe to work on. So that's this here. Older systems will have a much larger block that looks like this. And realistically, it's very similar in concept to a standard isolation T-bar for smaller loads, like you would see for, I don't know, a heat pump on the outside of a house. Now, on newer isolation pull-out handles, there's going to be 2 settings, in service and in short. The isolation handle offers 2 different options dependent on its orientation prior to insertion into the isolation block. So we then have 3 positions: operational, in short, and full isolation, which would be removed entirely. So if we go back to the system, operational would be with, obviously, the isolation handle in the in-service position. In short, the isolation handle is actually short-circuiting the output of the CCR here, which causes no problem because remember, this is keeping a constant current, right? So even if we don't de-energize the CCR, it actually doesn't cause any damage because the CCR says, well, we got to keep the current down low at, well, remember, maximum 6.6 amps, so it just ramps the voltage down. The advantage of doing this is that we close the circuit for the airfield lights. There could be 180 lights, and if you're doing troubleshooting and you want to find a break in the line, you're going to be using an ohm meter. And if you want to use an ohm meter, you got to make sure you have a closed circuit. An open in the CCR housing will make it a lot more challenging to navigate. Finally, full isolation would be removal of the handle entirely. And in this position, we could then work on the system completely de-energized, and there would be no chance of anyone getting a shock. Airfield lighting systems are part of a larger international standard. This means the terms, locations, colors, and positions of lights will mean the same in Vancouver, BC, Canada, as they do in Kuala Lumpur, Malaysia. This includes the brightness settings for the airfield lights. There are 5 brightness settings for airfield lighting systems. B5 is the highest current and the highest lumen output, as in 100% illumination of the lights. B1 is the lowest current and the lowest lumen output. Notice that it's not a linear relationship between current and lumen output. 2.8 is just under 50% of the current, and yet the lumen output is 0.2%. So it's not important for us to memorize every single one of these percentages, but it is good to recognize that B5 is always in relation to 6.6 amps, and that is 100% lumen output. Some airports will not have all 5, but they might have 3. So they go B5, 4, 3, something like that. In that case, then obviously you wouldn't have B1 or B2. But important to understand that the lowest number, B1, would be the lowest lumen output. And at 0.2%, you would be very likely unable to really see visually during the day that the lights are on. Keep this in mind because that could be a safety challenge if you thought the lights were off, but in fact it was on B1 setting. Now these brightness settings can be selected locally at the CCR by push buttons like we see here, or remotely by the air traffic controller from a touch display. Air traffic controllers typically observe and direct the airfield traffic from a point of elevation above the airfield, typically a tower. All airfield lighting can be controlled by the air traffic controller by a remote program, which then controls the CCR through a PLC. And so we can see here the runway and everything, and then on the bottom there's going to be settings that they can go through for all of the different lighting circuits that make up the taxiway, the approach, the main runway, and any smaller auxiliary runways. So the series isolation transformer ensures this primary and secondary currents are equal. So if we were at step 4 brightness, 5.2 amps, that would mean that there would be 5.2 amps on both the secondary and the primary. If the air traffic controller adjusted it down to B1, then that would be 2.8 amps, and we would have both 2.8 on the primary and the secondary. Now, if the lamp burnt out, there would be no current on the secondary, but it does not interrupt the primary circuit current, and that's because there is an individual isolation transformer for every single light. So if we look at an array of 5 lights, that means that 5 lights, 5 transformers. The series isolation transformer allows for individual lamps to burn out without the entire series circuit de-energizing. So here we have a burnt out light. There is no effect on the other lights there because it hasn't interrupted the primary circuit, which is the high voltage circuit. Now, if the primary voltage was not adjusted, the total primary circuit current would increase slightly due to the decrease in impedance. This would result in a rise in the light output, and that's simply just due to Ohm's law. R total is equal to R1 plus 2, 3, 4, and the total amps is equal to the voltage divided by the resistance. So if we don't want this burnt out light to have any effect on the other lights on the circuit, then we need to have a constant automatic source that will adjust the voltage to ensure that the current has not changed in the primary circuit. So The CCR will automatically adjust the output voltage so that the current is maintained. The process is automatically completed within milliseconds of a lamp burnt out. So let's take a look at that. So the CCR is going to adjust to a lamp burnout situation. Right now, it's cranking out 1200 volts, and we have 3 amps flowing in the primary. Let's say a lamp burns out. What does that mean? Well, it means that the total resistance of that loop will have dropped slightly. There's less load. So if there's less load, that means, well, in everyday electrical speak, you would expect the current to go down, right? But we don't want that to happen. So the total current will actually increase slightly. The light output would then increase slightly. And so what we would see is that the remaining lights would be slightly brighter due to the increasing current. So the CCR will then drop the voltage, so it's dropping it down to 1100. It'll bring it back down to the 3 amps, and that current drops us back down to the original level. Brightness of the remaining lights is maintained at the original level. Let's take a look at what happens if the system has a series circuit broken wire. So let's say we're operating at 4 amps right now and the lights are all on, but then, frost heave or maybe a backhoe operator or someone just inadvertently unplugged that wire and the circuit is opened. Well, the primary series circuit loops can be broken in these events, right? And that would be bad because current would drop to 0, the lights would go off. Now, this situation is considered highly dangerous for aircraft as no lights would be illuminated. And remember, the main purpose of this system is to ensure the safe landing of aircraft. The CCR will automatically adjust the output voltage so that the current is maintained. This process is automatically completed milliseconds within an open circuit. So let's see what happens. So we're going to adjust to an open circuit situation. We're at 3 amps right now. We're operating at 1800 volts. We got a circuit that's broken. 0 amps, lights go out. Immediately, what will it do? It'll ramp the voltage up to arc through the soil. The current now arcing through the current is now arcing through the break in the circuit, and all lights are operating at rated brightness because the current will come back up to 4 amps or whatever that value was. So look what's happening now. I've ramped the voltage up so high that it can arc through the soil to the other connector. And why it's permitted is because airfield property is not accessible to the public, and the primary purpose of the system is to land aircraft, not be safe for people on the ground. Now, no overcurrent trips. Is this situation dangerous? Heck, yes. And as we've alluded to, the airfield is highly restrictive. People should not be walking on the grounds, and the primary purpose is to land aircraft at any cost. Modern CCRs will log this event so that the maintenance person knows a problem exists and that we need to go and find that break. Runway lighting systems can be designed as single, dual, or multiple circuits interwoven. In this way, a loss of one series loop will not render the airport inoperable for aircraft landings. Here's another. It is good practice to ensure that separate conduits are used for each series circuit loop of wiring, which travels back to the CCR. If an arcing event takes place in one loop, it is less likely to damage all of the series loop home runs. So this here, if we had an arc in one of these conductors, it very likely could damage all of them. Whereas if we have them in 2 separate conduits, it's a lot less likely. Airport runway lighting systems have no personnel protections where overcurrents are concerned. No overcurrentable trip if a ground fault exists. This level of hazard is considered acceptable as this is restricted area. Overall, the purpose of airfield lighting is to ensure airplanes can land safely in adverse weather conditions or instrument assist failure. It is not designed to be safe for the general public or the electricians who maintain them. Unlike other types of electrical equipment, airfield lighting systems require almost constant attention, proper lamp alignment, elevation, level, as in, are they actually perfectly level with the grade? We may have to twist them so that they're facing the runway side because they have directional lenses. Replacement of fixtures, and that can happen due to de-icing equipment, snow clearing equipment, or groundskeeping equipment. Now, all light fixtures on an airfield for runway lighting must be identical in brand and model. If a fixture becomes damaged, it can't be replaced with anything other than what is existing on the runway. This is required because different fixtures will always have slight variations in light output. A single runway could not use different manufacturers or types or ratings of light. Replacement of the bulbs before they drop below 50% light output. When we newly install a light, it's going to have a humongous amount of light output. And as time goes on, that light is going to decrease. And so we can see here lumen maintenance curves, all sorts of different types of lights. Usually 50% lumen output is the threshold rating, as in we don't go any lower than that. We've replaced them once they are half as bright as they were when they were first installed. Now, light output can be estimated, and in that way we can replace all the lights once every 2 years. The other method would be to measure it with photometrics equipment. This type of equipment will actually GPS and locate every light, measure its value, data log it, and put it into a table. This is extremely expensive, and only very large airports have this equipment. Replacement of these bulbs, remember, they could be hazardous when you go to put the light bulb back into the fixture. Due to ground movement, frost heave, vibration, impact of aircraft, snow removal, lightning strikes, a high voltage source, anything, equipment damage can occur. Since the transformer could be damaged, it is good practice never to touch fixtures without high voltage gloves when the lighting loop is energized, as in B1 to B5. If we had acts for some reason, a primary shorted to the secondary, there would be high voltage available at the light bulb itself. If the primary shorted to the metal, we could have high voltage at the fixture. And so it's important that high voltage gloves are worn unless we can confirm zero energy and it's been locked out with that isolation handle removed. Cleaning of lenses is also very important. We have dirt, dust, insects, grass, all sorts of stuff. Cleaning of recessed in runway lights is also important. And I think it's fairly obvious why. This is an approach of a Boeing 747 jet. And watch when we land. Look at all the black. The touchdown zone of an aircraft is going to be covered in rubber. And so when they land, we need to clean those lenses once every month or however many landings is appropriate according to different airfield regulations. Here's a company doing that. And finally, wiring repair due to frost heave or wildlife. Cap tire, which is the type of flexible black cord that we often use in electrical, is really desirable to wildlife. Something about the smell and the flavor is desirable, and they like to chew through it. And because there's no overcurrent protection, that usually ends up with a flambéed critter. Now, the required preventative maintenance and recommended schedule of tasks is included in the CSA Z463 standard. This standard provides all the necessary details which are required for maintaining any electrical system in Canada, including airfield lighting systems. So why are we learning about this electrical system? Well, airports in Canada are largely run as a business rather than regulated transportation entity under the federal government. There may be minimal or no electricians employed at the airport itself. When electrical work is necessary, electrical contractors are brought in. Most contractors are not aware of the special hazards which exist around airport runway lighting when they arrive on site. Administrators of airports have minimal knowledge on the hazards that exist around airfield or runway lighting and assume all electrical work required at the facility requires the same standard skill set of a general electrical contractor. Finally, consider when the electrical system for the runway lighting would be turned off for renovation or upgrading. Almost never. A few of the documented deaths on airfields by electricians predominantly. In closing, never work on any portion of the lighting system unless the CCR is off and the isolation handle has been removed. Never use a tick tester to confirm if a series circuit is de-energized. Depending on the location of the circuit, it will not register. I can't make that, can't instill that strongly enough. It will not actually register depending on where on the series circuit you apply it. Never measure across a series lighting circuit to confirm if it is de-energized. There could be several thousand volts present. The only way to really confirm zero energy is to clamp a true RMS ammeter around the series cable. 0 amps equals 0 power, which equals safe. Never open a series lighting loop. Remember, even though the lights may appear off, they are not de-energized. Opening the circuit will trigger a rise in voltage from the CCR. Specialized training is available for airfield lighting systems through the Canadian Airport Electrical Association. It consists of a 2-week full-time course which takes individuals through all aspects of the airfield lighting system components, safety, and maintenance. Also, every year, CAEA hosts an industry workshop in a different Canadian city. Maintenance electricians from airports across Canada can discuss problems and solutions within this small niche community.